Hi folks, time for the second part on our visualization lecture on time and relative dimensions in space. This time we're going to cover space, specifically how you can visualize with spatial data and some of the ways that that's been done in the past. We are all familiar with visualizations of data in space. We call them maps. Not only just maps, but maps with overlays of data sets on them are a common part of our everyday modern life. Take, for example, this one is traffic data overlaid over the part of Sydney that the university is in. You can see at this point that there were pretty bad traffic heading north and east, but not so bad in other parts of the city. You might not be familiar with this visualization directly. It's something you probably see bits and pieces of every time you put in directions into your favorite Maps app. It will show you what the traffic conditions are like just along that route. It's much less interesting for the average person to see the traffic status across the whole of the city, because most of us don't drive on every road to get home. Just another example of how to adapt your visualization to the use case of your users. But I want to talk a little bit about other kinds of spatial map that maybe we don't encounter quite so often. This is a kind of colored regional map called a choropleth, which is a very fancy term for a pretty simple idea. You highlight regions of a map, in this case counties in the United States of America, and then you color them based on some data set. In this case, the blue indicates the percentage of people in that county who identify as black, and the red indicates the percentage of people who identify as Hispanic. You'll note that this is a two-variable plot, a bivariate choropleth, to use the scientific term. But this allows you to see red areas where there's a high Hispanic population, gray areas where it's mostly a white population, blue areas with a high black population, and purple areas where there's quite a little bit of both of the minority groups. And what I think is really fascinating about this, and this is something that you don't really realize until you start spending some time in the United States, is just how, I guess the word is, segregated it all is, right? The South, the deep South, is black, the Southwest is Hispanic, and everything else is white as anything. Demographics that we think about at a country level aren't really represented down at the local county level, with the exception of New York, Florida, Eastern Texas, and Los Angeles and San Francisco. There really aren't that many regions where there's a heavy population. Oh, I left out Chicago. Everyone leaves out Chicago. Poor Chicago. With the exception of those, there really aren't that many areas of the US with high populations of both black and Hispanic individuals. That story is only really told, only made starkly real by a visualization like this. You can realize why the middle states at the top there, the flyover states, can think that race isn't an issue in America, whereas the ones at the bottom can't seem to go a day without dealing with issues of race, because at the map level, things are not smooth, things are not uniform. Going to be a lot of US maps in today's, because there's just so many great visualizations of the difficulties and diversities of that particular nation out on the internet. Here's another example. This is a map of the counties, again, of the United States, another choropleth, that Donald Trump won in 2016. And what you can see in this map is that, looking at geography, it's a pretty conclusive victory, right? There's an awful lot of red here. In fact, this was posted on Twitter by some Trump fan saying, "Try to impeach this, like America's behind us." But this is one of the lies you can tell with spatial visualizations of data. There's a couple of things going on here. The first one is what your mapping is. In this case, they are mapping bright red or bright blue based on who got the most votes in that state. So they've already ironed out any real gradient between those two extremes. A county in which Clinton got one more vote is bright blue. A county in which Trump got one more vote is bright red. Interestingly, can anyone see some correlations between the colors in the previous map and the colors in this map? Maybe the more diverse areas of America tend to go a little bit more blue, but that's another story. So they've already got one piece of bias here. That is, it's winner takes all. And this is a huge problem with the US election system in general. A winner takes the entire county. And the other bias here is a natural problem with choropleths, with representing data at the county level. And that is, the size of the county, geographic size of the county, distorts the actual vote totals. Let's have a look at what happens when we instead make the size of each region of this plot based on the population. That is a much more realistic picture of partisanship in America. Now, it looks like a bunch of blue, solid blue enclaves surrounded by a desert of little red dots. Because, of course, all the rural counties have very low population, but tended to go Republican. In urban areas, tends to go blue. In suburban areas, it tends to go red. And then out in rural areas, it's red, but the population is very, very small. This is the lie that you can tell with a choropleth. Benjamin Disraeli said about 150 years ago, he was Prime Minister of Britain. His story is not germane here. He said there are lies, damned lies, and statistics. In this course, we're focusing on the worst one of those, statistics. You can map your data in a way to tell your story, but at a certain point, translating your data becomes manipulating your data. Representing what you're doing becomes deception. If your data is not really caring about the square kilometers, or I guess in this case square miles occupied by a region, then maybe it's not a good idea to represent your data using the size of counties. Because people perceive, remember back to the video on mapping that we did, people perceive area as a very, very salient pre-attentive variable. Once you see a big red thing, you're like, oh, that's big. Even if its size has nothing to do with the argument being told. That can confuse a user if misapplied, or deceive a user if done deliberately. It's something that you must be aware of as a designer. There is no true visual representation of your data. You had to transform your data from a big table of numbers into a visualization, spatial or otherwise. It is incumbent upon you to make sure you're neither embedding lies, damned lies, or statistics. We talked a lot in the previous video, not just about bias, the previous video, the temporal video. We talked about uncertainty. And uncertainty is also something that comes up in spatial contexts, most famously in trying to predict the weather. Here's a visualization that shows both spatial data and temporal data and uncertainty. I really shouldn't have said both if it has three things, right? This was Hurricane Irma that hit Florida in September 2017. I mean, it first hit a whole bunch of places in the Caribbean, but news articles tend to come from the US, right? So everybody seems to remember it as the hurricane that hit, or almost hit, Miami. Hundreds of people died, and many, many more were flooded without power or forced to flee their homes. This visualization shows the orange dot of where the hurricane was at the time it was made. This was made by the National Hurricane Center in the US. The shaded light gray area shows where the hurricane will probably be over the following 3 days. And then the dotted blue and white area shows the much less certain area it will be in the 3 days after that. So that's the day 4 to 6 forecast. Because of reasons involving maths, it is very, very difficult to predict the weather. Small changes can compound into large effects, and those sorts of things mean that a slight difference in your forecast can lead to a huge difference in the output. This is called chaos. I think it's fascinating, but it's not the subject of this course. So there is a great deal of uncertainty in the prediction, even immediately, right? The hurricane is probably going to follow that path. That's based on the predictions that people are making, but it may deviate a little bit. So hurricane warnings are issued for the red area. That's effectively a choropleth, right? It's highlighting areas of a map based on some status, in this case whether they've been given a hurricane warning. Then the pink areas are hurricane watches, so that's not quite the same level of disaster as warned, and the and the blue areas indicate a tropical storm warning, which is still pretty bad, but primarily about swell and flooding and coastal areas only. There's a huge amount of data here because it's not only showing one level of uncertainty for the prediction in the next couple of days, but then even more uncertainty for what's going to happen in the couple of days after that. It takes supercomputers, huge amounts of supercomputers, to produce these predictions. This is a model, just like we were talking about in the temporal video, a model of the future, but while it's complicated to predict the unemployment or the economy, it is absurdly complicated to try and predict the path of a hurricane. What tends to happen is that what you just saw is the composite output of many models and many experts and many supercomputer hours working together to do the best that they can to be accurate and precise, where accurate means close to truth and precise means as certain as possible, so to minimize uncertainty. What's actually going on under the hood is something a little bit like this. This shows the path, the most likely path that hurricane could have taken, the same hurricane, Irma, back in 2017, along about 20 different meteorological models. Note that this is called a spaghetti plot. It's showing the path on a map of many different things, in this case many different predictions of a hurricane, all starting from that same point where it was on Wednesday the 6th of September, I think, and then showing it move. These predictions are based on wind strengths, are based on historical hurricanes, are based on what is known about the region and the water depth and the air temperature and the water temperature and the wind and the coast and what kind of rocks they're made up from and how big any mountains are. The amount of variables that go into these predictive models is staggering. And yet, even with all the best meteorological brains in the world, the models deviate a huge amount because chaos is just a big deal. See all the technical things you learn in this subject. Chaos, a big deal, says lecturer. To make any sense of this, to know what all these models mean, to know how you should average them together, this requires a degree in meteorology, which I certainly don't have. But many predictions of these sorts of things are made, capturing spatial data and temporal data and uncertainty. Here's one that I think is quite interesting. This is from 538, what was originally a politics website that has branched out into a whole bunch of other things that involve data and prediction, sport, weather, etc. This shows the same thing, again, Hurricane Irma's path, this time starting a day or two later in September 2017, and showing it predicted. The path is the black line, the current position is the black dot, the predicted path is the kind of balloon-shaped dashed area, showing that in this case it will probably directly impact southern Florida. For those aware of the geography of Florida, that's where all the people are, and they all live in coastal areas where things got pretty bad. This one also shows the historical path. This is an attempt to make what's going into all those mathematical models more understandable to a human. This is an attempt to explain some part of the models. That is, the models know a lot about what happens when hurricanes sweep up across the Caribbean like this. They go across the northern Caribbean, they sort of graze Dominican Republic and Cuba, Puerto Rico, and then they often hit Florida or sweep up the northeast and go along through the Carolinas and up to New York. These are the previous paths of some of the worst storms on record, showing strength as a width. This is the same kind of visualization as, if you remember way back in the original video, was used for Napoleon's armies. It's a flow line showing the thickness of the line as a variable and that then thing moving in space. In this case, the thickness of the line is mapped to the speed, the wind speed of the hurricane. That is the speed of the wind spinning around rather than the speed at which the hurricane's going forwards. Hurricanes being a cyclical storm core. And you can see many hurricanes smash into the southern tip of Florida for reasons that probably make sense if you're a meteorologist, but I'm not. Many hurricanes with very high wind speed have followed this path before. This article is trying to tell you a story. It's trying to say, take this seriously. You have a day, maybe two, to get out of your home, to evacuate to higher ground, further away from the storm, further away from the flooding. A number of people died when this storm hit Florida. Thankfully, it didn't make landfall directly at Miami, but it did a lot of damage. These visualizations of space and time, already quite complicated concepts that try to help people get a grip on uncertainty, which is something that humans are notoriously bad at grappling. See the stock market for examples. Hopefully helped reduce the complexity of all those meteorological predictions and hopefully helped save some lives. This is a story about turning data science into data design to help people. This is exactly the kind of thing that we are here for in this subject. Of course, when it comes to grappling with uncertainty and when it comes to grappling with all of these complex predictions, sometimes people don't make such great decisions. Sometimes some absolute idiot just draws on the map with a Sharpie and says, look, it might hit Alabama. But the less said about that, the better. What I know you will do is take some of these complicated ideas about visualizing time, visualizing space, and visualizing uncertainty, and by the end of this semester, be able to do something a little bit more advanced than draw on a map with a crayon.